Okay, so this is Chemistry 108, Chemical Principles 1 at York College. Today is March 19th, 2015, and we are starting Chapter 5. Chapter 5 is on gases. Right, Chapter 5 is on gases. So what we're going to do now is learn about properties of gases and learn sort of information about gases, right? Gas is one of the three phases of matter. The others, of course, being solid and liquid. The thing about the material in this chapter is don't forget what you just did, right? In terms of moles and molecules and reactions and limiting reactants and balanced equations, because once you learn about all the properties of gases, we're going to learn about reactions, and we're going to do stoichiometry with gases, right? So if you if you learn that very well, retain it. If you don't think you're that strong on that still, you're going to need to get up to speed, right? Because the rest of the course we're going to be doing things with moles, right? We're going to be doing things with with balanced chemical equations. We're going to be doing things with molar masses and that kind of thing. So, properties of gases. We covered gases very briefly, probably back in chapter 1 or so, when we talked about the different states of matter. Right, gases don't have a fixed shape, and they don't have a fixed volume. They take the shape and volume of their container. That's basically what we looked at, or how we defined gases the first time. Gases spread to fill whatever container or whatever room or whatever space that they can until they're blocked. Right? Gases can be compressed, right? So because they can spread, if you push against them, they can compress. And what does that mean? That means between the individual molecule, there's lots of empty space, right? And so if you have a gas, we'll take right, here's a container, and if you have your gas, there's lots of space between the molecules. And so if you have a container like this with a kind of like a cylinder with here's kind of a movable piston, right? So what you can do is you can take this and push it down. You push it down from here to, say, here. What's going to happen? These molecules are going to get squished. They're going to become closer together. The volume's going to become smaller. The number of molecules doesn't change. They just have a smaller space in which they can bounce around. And so they get squished. That is, in fact, a very scientific and technical term. Because of this kind of thing where the gas molecules are able to spread freely, gases are able to mix freely with other gases. So if here we have like argon gas in pink, and here in the white we have neon gas, the molecules are both going to spread out to fill the space here. And so they're both, and when they do that, they're going to intermix with each other evenly. And so those are kind of basic properties of gases. If you have gases in a closed container, those gas molecules are going to be moving around, and they're going to, in some cases, bump into the walls of the container. And when they bump into the walls of the container, they exert a force. Right? Just like if you were running around, you rammed into the wall, you would exert a force on the wall. And that force gives rise to a quantity called pressure. Right? Pressure, technically speaking, is force over area. So over a specific area, how much force is being applied, in this case, by the gas molecules. Can somebody think of a context in real life where you encounter pressure of a gas? Yeah.
Like cooking, like a cooker?
How so? Maybe.
Like if you're trying to boil water or something, then you pressure.
Okay, yeah, so they have these things called pressure cookers, right, which seal basically very tightly and hold in all the gases as you start to like boil your water or something. Another one? Anybody? Yeah.
How about soda?
Soda, right? So there's gas in the bubbles, right, in your soda, and so it exerts a pressure. And actually, if you ever really kind of did this to a brand new bottle of soda that hasn't been opened, you can feel it. That's because there's pressure being exerted at the top, right, the little space between the soda and the cap, and that's making the hole basically pushing on the container. Does anybody drive? Yeah. So what do you have to what do you have to watch out about your tires? You have tire pressure, right? If you drive over, you're going down Jamaica Avenue, you drive over a small nail, and you might get a flat right away. That would be very bad. But you might not. You might just get a slow leak, right? And then the air kind of comes out of the tire, and the tire gets soft, and it's not so good. The pressure goes down because there's less air inside. So pressure can be measured in different units, just like length can be measured in, say, feet or inches or meters or centimeters, or so on, miles. Pressure can be measured in different units. One of them is called the atmosphere. And the term atmosphere comes from the fact that there's air all around us, right? The atmosphere is kind of the air all around us and all around the Earth. And there's a force, a gravitational force being pulled, that's pulling the air molecules, right? We don't feel it because it's kind of all around us, inside us, outside us, all around us from every direction. And so we feel it the same on every side, and it kind of cancels out. But there is indeed a pressure, right? And so the force of the air pushing down, the amount of that force is called 1 atmosphere. So atmosphere is kind of a more geological term. The pressure from the atmosphere is 1 atmosphere. Yeah.
So when you go up in the mountain, do you think the ocean is more pressure or less pressure?
Well, if you go up, what do you think?
More pressure.
It's actually going to be less, right? Because there's less air there. If you go deep in the ocean, then you have a second thing going on, right? You have the water. But if you were to go like really down, it would be more. Yeah.
Wait, why is it that when you go up there's less pressure? I mean, don't like oxygen like train at high altitudes because of the high pressure, so they have to conserve their oxygen levels?
No, it's because they train at altitude actually because there's less air there, right? So, so what happens is, in order for their body to get the same amount of oxygen, they make more red blood cells, that carry the oxygen. And so they're able to get, because they have more of these, they're able to get more of the less air that's there. Does that make sense? Right, there's less air there, so they need to get a greater proportion of the oxygen, so they increase their red blood cell count. And so then when they come back down to normal altitudes, then they have extra, right? They have more than they need, so they can run longer, or, ride your bike faster or whatever. And so here's another unit that's used to measure pressure. It's called millimeters of mercury. And the reason for this kind of strange terms, millimeters of mercury, is because way back in the day, people actually measured pressure this way. They took a pool of mercury. Now, mercury metal is one of the very few elements that's liquid at room temperature. Right? And so it's a liquid metal. And mercury is quite toxic, so these days we don't use it very much for, well, if we can avoid it, we avoid it. Used to be that there was mercury in thermometers. I mean, there still is, but only for kind of more specialized kind of applications. But what would happen is if you took an evacuated tube with where all the air had been sucked out, and you put it into a pool of mercury or a dish of mercury, the atmospheric pressure would basically push down on the mercury and push it up the tube. Right? And when it went up the tube, it would reach a certain height. And it would reach that height regardless of like how big the pool of mercury was, or to the first approximation, how wide the tube was, or how long the tube was, right? If it was longer, there would just be more empty space at the top. That height was always the same. And that height turns out to be 760 millimeters, which is the same as 76 centimeters, which is the same as 0.76 meters. Right? And so 1 atmosphere of pressure equals 760 millimeters of mercury. And so just to reiterate, 1 atmosphere is kind of the normal pressure at what they call sea level, right? The kind of the oceans all around establish sea level. And as you go up, you go down, it changes slightly. Also changes with the weather, right? This is the thing that most people don't really understand or follow when the weather report comes on the radio. And they say, you know, the pressure's at 30 inches and falling or something, right? That has to do with this, right? And so they're measuring they're measuring in terms of inches rather than millimeters and so on. It's all very kind of interesting, and if you go take your geology class, you'll learn something about it. So this is where this term comes from, the millimeters of mercury, but it also becomes a unit to measure pressure, right? So pressure is greater than atmospheric pressure will be greater than 760 millimeters of mercury. Pressure is less than 1 atmosphere will be less than 760 millimeters of mercury. 1 atmosphere. And this actually can be used as a conversion factor if I wanted to convert units from atmospheres to millimeters of mercury. So here is, okay, let's not do this just yet. Should we do this now? Yeah, let's do this now. Okay, so here's a kind of interesting, don't look at that formula, I don't like that formula. Here is a, what's called a U-tube manometer. This is the original U-tube, right? And what you have is a bulb here with a stopcock. So you can either close it, in which case the tube and the gas are separated, or you can open it so the tube and the gas are connected, and whatever gas is in here can go into the tube. And so here we're showing that the U-tube has an open end, and it's open. If it's open, that means it's open to the atmosphere. And so whatever the atmospheric pressure is, typically 760 millimeters of mercury, or 1 atmosphere, right, is going to be pushing down. And the gas on this end of the tube, right, and the gas is going to be, once the valve is open, it's going to go and push down on this end of the tube. And what is it pushing on? Well, it's pushing on a column of mercury. And so the way I like to view this kind of device is that the atmosphere, the air, and the gas in the bulb are kind of competing with each other. If we assume we're at sea level and the temperature is normal and everything, this is going to exert a pressure of 1 atmosphere, which equals 760 millimeters of mercury. If the gas in the bulb has a pressure greater than 760 millimeters of mercury, you're going to have a situation like this, right? Because there's basically two gases competing. One of them's pushing down at 760. One of them's pushing down, in this case, even harder or with more pressure than 760, and so it's winning. Right? It's pushing it down and pushing the other side up. So what's the pressure in here? Well, it's going to be 760 millimeters of mercury plus whatever this distance is in millimeters. And so let's think about this for a minute, right? Oh, you weren't supposed to see that. Okay, so let's consider this guy over here, right? This first YouTube, this first manometer over here. It has an open end, there's some gas here, and here's the column of mercury. If we say that atmospheric pressure is 760 millimeters of mercury, what's the pressure of the gas in the bulb? How can we do this? Well, we can do this by saying this gas has some pressure, and it's competing with atmospheric pressure. And who's winning? The gas in the bulb or the atmosphere? The atmosphere is winning, right? Because the atmosphere is pushing down harder than the gas is pushing, right? It's pushing down harder, so it goes lower. This is pushing down less hard. It doesn't go as low. So the atmosphere is winning. It's winning by how much? Oh, we're supposed to do this. It's winning by 52 centimeters of mercury. So what's the pressure of the gas in the bulb? It's going to be 760 minus, well, this is centimeters, not millimeters. If we do the conversion, 52 centimeters equals 520 millimeters. If you don't believe me, you can check, but that is correct. This is going to be 760 minus 520. Millimeters of mercury, right? Minus 520 millimeters of mercury gives me 240 millimeters of mercury. What about this second one over here, this one in the middle? Which is the pressure greater or less than 760? Who thinks it's greater? Who thinks it's less? And who doesn't think? Very good. The doesn't think, I think, wins. What? I just by the number of people. So somebody who thinks that it's greater, the gas is greater, explain. Well, you thought the gas was greater, right? So why do you think the gas is greater?
It's pushing the mercury further up.
Right, because it's pushing the mercury further up. So this side is pushing harder than this side. Right? This side is pushing harder, so it's because it's pushing down, right? So if it's pushing down harder, it's pushing the other side higher. So this pressure is greater than 760, and it's greater by how much? It's greater by 67. So what's the pressure? The pressure is 760 millimeters of mercury plus 67 millimeters of mercury, and that's going to give me 837 millimeters of mercury. So that's going to be the second one over here. Now, the third one's a little sneaky. Right? The third one's sneaky because it says it's got a closed end. Right? These have open ends. They're open, so open ends means they're open to the air. They're open to the atmosphere. The closed end means it's not open to the atmosphere. What's it feeling? It's only feeling the gas on this side. What's it feeling on this side? But it is feeling the weight of the mercury. But what about the gas pressure? Nothing, right? We're going to assume it's evacuated. It's nothing. So this side is always going to win. unless this is also nothing, in which case it'll be tied. But this side is going to win, and it's going to win by how much?
103 millimeters.
By 10.3 centimeters or 103 millimeters. And so what's the pressure in this tube?
760.
I mean in this gas. Sorry?
760
There's no 760. It's not feeling anything. On this end it's 0.
So it's going to be 103.
So it's going to be 0 plus 103 millimeters of mercury, which of course equals 103 millimeters of mercury. You got this. Let's do one more before we wrap up. Okay, so that's not like a deformed elephant. That's okay. So this is open, and let's say the atmospheric pressure is 760 millimeters of mercury, and the pressure here is 800. What's the distance here? Millimeters of mercury. Very good call. Numbers and units. Thank you. What's the distance?
40.
It's going to be 40. This side is lower. This side is higher. That means this side has a greater pressure. It's greater by how much? 800 minus 760. 800 minus 760 equals 40 millimeters of mercury. So that's going to be 40 millimeters. Okay, so we are done here for now. Go work on chapter 5 and see you on Tuesday.